and I hope it starts. Right. So the next half of the class, okay, we are going to look at the elastic curve technique. Okay. So the first part, we just look at the integration method. Okay. I show you guys boundary conditions, how to apply integration method, okay, and forming boundary conditions. Now, next we are going to learn, not learn, but apply, okay, deflection, or we are going to determine the deflection of beams using the elastic curve method. Okay, the elastic curve method. So we are going to look at a structure that is simply supported. Okay, so this is our structure simply supported at point A and at point B. Okay, and then we are going to put a force, a point load, a certain distance away. So this is our P. Okay. Then from here, I'm going to draw the deflection. So this is the loading condition. We're going to draw the deflection or sketch out the deflection pattern. Okay. So I'm going to have an axis. So this is our Y. Y over here represents our deflection. Okay. Then over here is our X. Then we have point A here. And this is point B. Okay. I don't know why I focus on the positive, because the deflection will go on the negative side. All right. So how this beam is going to deform, I'm going to sketch out now. Okay. So it's going to deform like this. Okay. So now this is deformation or deflection. Right. So hold on. I'm going to switch off my fan. Okay. So that is the deflection. Okay. That's the deflection. So we want to find, right? We want to find a point over here, right? We are going to look at the point over there. And that point, okay, has a certain distance, x. Okay. Now, some of you will say how you notice that point is an arbitrary point. Okay, arbitrary means it can be anywhere. So if this is your x, right, what we have now, the distance from here to here, now this is our y, which represent again our deflection. Okay. And not just that, if I were to sketch a gradient at a point, okay, a tangent, sorry, not a gradient, a tangent. right? Right. So the tangent over here will be our slope. Okay, so theta is the slope. So that is what we mean by slope. Okay, that's what we mean by slope. So in order to find the slope of and deflection, okay, so in order to find the slope and deflection, okay, we apply the elastic curve method. I'm not going to derive it again. I'm just going to give you the final form. Okay, so the final form is what? EI d squared y over dx squared is equal to m as a function of x. Right, now this moment as a function of x, you've seen a lot already. You all know how to apply or how to get it already. Yes or no? Okay. So this equation over here, right? This equation over here that you see is known as the elastic curve method. So so let me define what they are first. E is our Young's modulus. I is our second moment of area. Okay, and m x is the moment as a function of x. Okay, right. So as I mentioned earlier in the class, yeah, the deformation pattern is exactly the same. Only now, Justin, the only difference is you now know exactly, okay, how much deflection is there at a certain distance. Okay, it's not just a pattern now. Now you know specific points. Okay, right. So now you can see, right, how we can get our slope and deflection. Okay. Now I want to bring you all back to over here when we just started. Is it here? Yeah. I will I will copy this whole thing. Yeah, and I will put it over here. Yay. Okay. So coming back to this flow again, right? Right. We get our dv over dx is equal to minus omega x, right? We integrate the first time, we get our shear force. We integrate the second time, we find our moment. Then after that, before we go there, we're going to what? Apply the what? Elastic curve. This elastic curve and this elastic curve are the same. Then we integrate the third time, we get our slope. We integrate our fourth time, we get our deflection. Okay. So we realize that when we integrate 4 times, right, we have 4 constants. So the final form, okay, let me write the final form for you, right? So it's the final form. When we integrate, is equal to EI y. Okay, let me go one step back. Let me start from the moment equation, right? So moment equation is equal to m as a function of x, right? Then we have our minus omega x. Then we integrate twice already. Plus by c1x plus by C2, right? Then we apply, okay, when I say apply the elastic curve, okay, this is where we, right, this whole thing is equal to EI d squared y over dx squared. This is where we what? Apply the elastic curve. So the next time, then after that, we integrate again. Now is the third time, right? Integrate the third time. So you get EI dy by dx is also equal to EI theta, right? So you have 1, 2, 3 minus omega x 3 times plus by C1x squared divided by 2 plus by C2x plus by C3, right? Then we integrate again. So this one you get the what? You get the slope, okay? And finally, you know what? I'm going to move this up. And then finally, we have EIY, okay, as a function of x. So we now integrate what? 4 times. So with this method, now you know this method, we don't need to assume what? Remember the first week or the second week? Is it first or second week? We assume the body to be what? A rigid body, yes or no? Now we don't need to assume the body to be rigid body anymore. We have moved on. Right? Right now you know at a certain distance what is your deflection now. Okay, we don't need to make the assumption that it's a rigid body. Okay, so now what I want to highlight is now how many boundary constant do you need to find? 1, 2, 3, 4. So therefore, I'm just going to write over here. So therefore, 4 constants to determine, which is our C1, C2, C3, and C4, right? So therefore, 4 boundary conditions are required. Okay, we need 4 boundary conditions that are required to solve for it. Okay, so now we are going to look at an example again. Okay, we're going to look at an example because this is again just integrating. Okay, just integrating. Okay, so no doubt we can say, okay, let's stop the class. Okay, let's give you some equations and you go boom, 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 you're done. Yeah, but I don't think that's the way. Okay, we hired a previous instructor that did this. Okay, for this part of elastic curve, he finished the whole course in 10 minutes. Okay, and yeah, I had so much complaint. So let's look into an example also. Okay, some of you will ask me the previous instructor, what was the class average? Anyone want to ask that? No.
Class average.
The class average was as bad or even worse. But students were complaining he just show us equation and want us to solve without solving himself. Okay. So this is point A, point B. Okay. So let's work this time where it is simply supported. Okay. And let's have a triangular load. So there is omega naught. Okay, so now we're not going to work with numbers. We just know this is omega naught. And the distance from here to here is L. Okay. So we're going to find we're going to find the deflection Yeah, we can find the deflection